Good morning, welcome to this lecture. My name is Alessandro Golkar. I'm an assistant professor at the Skolkovo Institute of Science and Technology. And this morning I would like to talk about this lecture on what is system architecture and why it's important for the development of complex engineering systems in space. I would like just to summarize what we've been talking in this part one. So we talked about systems thinking and why it's relevant to the design of complex engineering systems and infrastructures. And what I really cared about here is the concept of emergence and complexity. So what is emergence? Well, it's the reason why we do system architecture. And what is complexity? It's really the price that we pay for having that emergent behavior happening. And we just commented a little bit about architecture, what it is, what is functions, what are forms, what are interfaces, and what are relevant. And in particular, that most of the magic of system engineering happens at interfaces. So now in this part two of this lecture, I would like to talk about some of the quantitative tools that are used to do system architecture at a very early level, what I call trace space exploration methods. The learning objectives of this part are three. First is to understand the purpose and learn the fundamental approaches of trace space exploration as a part of the life cycle management process. The second one is the application of trace space exploration to support the formulation and selection of architecture in systems architecting problems. And the third one is to learn how to properly formulate a trace space exploration model. Now, of course, this lecture does not have the pretense to teach everything about the subject, but rather to give an introduction and pointers for people who are interested in learning more about this fascinating field. Well, first of all, let's see, how do you define an architecture? So as we said before, what is architecture? Architecture is the embodiment of some concept into some set of functions, right? Which then are realized by the design of hardware system, which is made of form, right? So physical systems. So to summarize, form is really what the system is, right, in reality, and function is what the system does. From that, well, you define a concept, right? Concept means map functions to forms, and then you do trace space exploration, which means to define what are the architectural decisions and explore the trace space of possible architectures that you can realize by choosing different options for those decisions for functions and forms. So some examples of functions and forms. Well, if you take, for example, a rover system, function of a rover system is to explore, right? So to explore a planetary surface, to gather science data, to, for example, generate pictures for media outreach, and so forth. What are the forms? Well, for example, having cameras, science instruments, having the hardware platform, the wheels, and those are interfaced to each other to create the rover system, right? So there are several emergent behaviors that occur, and the complexity you have to pay is, for example, how the system is going to work with the entry, descent, and landing system, and how those are going to fit into the launch vehicle you have available. When you go from system architecture to trace space exploration, how do you connect the two? Well, first of all, we said, architecture is really a process of synthesis, right, that aims at generating and selecting system concepts. We saw in part one a little bit how creativity and how the architect play fundamental roles in the system architecting process. It's really a heuristic discipline. It's not something, let's say, methodic in a sense of linear step process. Now, with trace space exploration, we put a little bit more structure and a little bit more method into this process. So trace space exploration is a tool, it's a systematic approach to do system architecture, okay? So whereas architecture is synthesis and engineering is analysis, trade-space exploration is a hybrid of the two. It's a hybrid of a synthesis and analysis process. And it's a support to system architects because it allows them to generate and select concepts when complexity and the number of feasible options of feasible architectures, they mandate the use of computational analysis. So this is oftentimes actually the case in real-world systems. If you think at, for example, Mars sample return mission, so the mission to retrieve samples from the Martian surface, there are thousands and thousands of ways on how to do that. If you actually enumerate all the possible architectures available, I will comment on that and how do you do that and how do you identify all these possible options. Of course, in traditional engineering process, you cannot examine in detail all thousands of them. You have to choose the 4 or 5 or less, depends on how much money you have, but choose a very restricted set of those that make sense to you and with which you're going to work more in detail. So how do you choose them? Well, trade-space exploration gives you a tool on how to choose those preferred architectures. What is a trade space, first of all? Well, trade space is the set of alternative system architectures that satisfy a set of system requirements. Okay, so there are some requirements that are set up front, which are basically derived from stakeholder needs, which you validated with the stakeholders and form the basis of the analysis. And from that, with the approach that I'm going to explain in the next minutes, is a way to enumerate all these possible architectures that comply with those requirements. The reason why it's called a trade space, the first part of the word trade, comes from the fact that there are trade-offs, right? So typically architectures, the ones that are good, they trade off one quality for the other, right? So for example, it's impossible to have the highest performing system for the lowest cost, right? Otherwise, everybody would take that if that existed. Typically, you have a trade-off, for example, between performance and cost. And there are some architectures that have better trade-offs than others, that give you more performance for the same money, basically, right? And it's not just about performance and money, it's not just performance and cost. There are also other things associated, we're going to talk about this. Basically, to summarize, trade-offs are balances that occur among contrasting objectives, right? That are displayed by alternative architectures. Some examples, again, of contrasting objectives. I mentioned one before, performance and cost. Another one, if you take, for example, from everyday life, a mail shipping method, if you buy something from the internet, for example, you can either choose to have a quick delivery method for your items, right? But it's going to be expensive. Or you can have something that is inexpensive, but it's going to take more time. So you can have, postmen walking, maybe not effective. You can have airmail, you can have trucks, you can have air freights, you can have cargo trains, right? And all of them have different qualities associated. For example, some of them impose you some, size limitations on the package you can ship. Some of them are more expensive, some of them are cheaper, some of them are faster, some of them are slower, right? What I just illustrated to you is a possible, very reduced set as an example of trade space, right? So different possible architectures with which you can do shipping. For trade space exploration, I propose a framework which is composed of 6 steps. First one is formulation. So how do you formulate a trade space and how do you explore it? Number 2 is enumeration. So starting from the formulation that you have, how do you go about enumerating all the feasible architectures that are inside that? The third step is evaluation. So once you enumerated all the possible architectures, how are you going to go to evaluate them, right? On all the different metrics. Number 4 is down selection. So once you evaluate them and you know how they rank among the different objectives, how are you going to choose the ones that have the, what we called before, best trade-offs? Number 5 is analysis. So the process of analyzing your results and understanding what I would call the physics of the trace space. How does it work, and is there any fundamental message that we can derive from the analysis? And number 6, visualization. Typically, as I said before, you're involving a medium-sized trace space. It could be thousands or tens of thousands or hundreds of thousands, also millions, and large trace spaces involve billions of options that are ranked maybe among multiple metrics. How are you going to go to visualize the results to make the message clear to you first and then to your audience, the engineers and stakeholders? So in this presentation, I would like to discuss the first 4, formulation, enumeration, evaluation, and down selection, which really form the core of the method. And I will point to other online resources or textbooks that can talk about analysis and visualization. So let's now talk about formulation. How do you go about formulating architecture? A trace space can be defined as a set of interconnected decision variables. This was the subject of Bill Simmons' thesis at MIT a few years ago, in which he said that you can represent an architecture as a set of decisions and parameters. Those decision variables are variables that uniquely define system architecture concepts. They must not be confused with design variables, because decision variables are those that are related to architecture, and design variables are those related to system design. As an example, if you take an engine, an engine architecture means to define, for example, if it's what is the thermodynamic cycle behind the engine. Is it Otto cycle, Stirling cycle, whatever that is? That's a decision variable. Design variable would be, the hot temperature of the combustion chamber, right? And if you use hierarchy, as I presented in part 1 of this lecture, you understand that one is an architecture level decision and one is a design level decision. We want to focus on the first one. Parameters, they are fixed throughout the trace space, and basically they represent your assumptions, which reflect your system requirements. If you want, you can change them during the analysis to understand what is the effect on the trace space, but typically they are fixed. So every architecture that you're going to generate, evaluate, and down select, they're going to have all the same parameters. As an example, from the mail shipping process that I explained previously, decision variables are, for example, whether carrier type, air versus truck versus train, the supply chain structure, whether it's a hub and spoke, whether it's a distributed network. These are decision variables, right? But for example, the size of the engine of the truck, or the fuselage length of the cargo aircraft, or these are more, let's say, design variables, they're not decision variables, right? A meaningful parameter in this example could be your daily throughput, your shipping capacity. Let's say, how many tons of mail can you ship per day, right? That's a meaningful parameter to keep it fixed. So the purpose for for thinking about formulation is to efficiently define an architectural trace space. Why do I stress the word efficiency? Well, efficiency leads you to the principles that I explained previously, right? So leads to a clear, non-ambiguous, accurate, computationally affordable, and exhaustive definition of the trace space. Efficient trace spaces are such that they can be enumerated and characterized in a minimum time possible, and consequently with the most efficient use of your computational resources. As you will see later on, trace space exploration involves a lot of coding and computational processes, and to have an efficient formulation in some problems can be critical. Non-efficient formulations, in fact, they may result into unsolvable, ambiguous, inaccurate, and non-exhaustive formulations. What about efficient formulations? Well, a few words more. Well, first of all, if you have efficient decisions, they enable the identification of the primary design drivers and expected architectural trade-offs. So if your decisions are efficient, they do this, right? So they identify what are the primary drivers of your architecture, and they will be able to capture the trade-offs, right? Efficient decisions typically are non-redundant, so they don't overlap with each other, and they capture different aspects of the architecting problem in an efficient way. Third heuristic would be that an efficient formulation is a complete representation of the architectural problem, right? So a decision set that makes sense is complete. And fourth and last, an efficient formulation represents the architectural problem using the minimum possible number of decision variables and options, right? Because otherwise, there are cases in which, let's say, a large problem can be formulated using a very inefficient formulation, then you're not able to solve it, and then you're not able to do your work in space exploration. So you really have to use the minimum amount of information required to represent what you need to represent. Now, let's talk of step number 2, enumeration. Again, in the first step, what you do, you formulate the architecture as a set of decision variables, and for each decision variable, you enumerate possible options, right? In step number 2, let's say you start from this table, right? You want to enumerate from this decision variables and options all the possible combinations that make sense, which automatically means you're introducing some feasibility constraints, for example, compatibility constraints. Well, before going into detail, I just want to mention that enumeration can be either full, exhaustive, or partial. So it's the same in mathematics you have in combinatorial problems. You can either have an exhaustive enumeration of the possible combinations or a partial one that is guided by some principle, right? So in full enumeration, basically you have the advantage of being able to see everything, and it gives you an advantage of analyze the structure of the trace space, right? Which is really important to understand what they call the physics of the trace space. And also, I would say it's very straightforward implementation. It's brute force. You take all the possible variables, decision variables, all the possible options. You just enumerate all combinations. In a sense, it's easy, right? Problem is that this type of analysis you can only apply to very limited cases, when the trace space size is limited. With modern computational capabilities, typically this means that the number of options should not exceed the millions. Okay. But it's very often the case where you have to deal with problems that exceed billions, right? So full enumeration in this case is not going to serve you at all. So in that case, you want to resort to partial enumeration, which allows you with some logic, right? So you can use some artificial intelligence logic, you can use some decision analysis logic or some heuristic logic. You can explore very, very large trace spaces, but there are some cons, of course. Well, first, is that you get much less information on the structure of the trace space, unfortunately, with respect to the full enumeration. It's more sophisticated to implement. It really goes into an art sometimes, especially with heuristic algorithms. And whereas with exhaustive enumeration, you can really build some guarantee on the quality of your result, in partial enumeration, this is much harder to do. So how do you do enumeration? Well, enumeration can be done by representing, for example, an architecture with a vector that takes all the design decision variables, right? And on each component of the vector, you have one option of the decision variable, right? So as you can see in the slide, you can take vector x, there are different components, 1, 2, 3, 4, and they represent a different option of your architectural decisions. So as you can see here in the slide, you have decisions on the rows and architectural alternatives on the columns, right? This is an example of a launch vehicle. First decision here is number of stages. Second decision is propellant type on the first stage. Third decision is the propellant type on the second stage, and so forth. And basically, you represent an architecture by picking up an option from this table, from each row of the table, right? So in the example here, I highlighted this very simple example of 3 stages with 3 different propellant types, and as you can see, you can translate that into a vector, right? In a vector that represents your architecture. So design vectors. Now, of course, there is much to talk about them, right? In system architecting problems, typically are discrete vectors, meaning they represent a discrete set of options, right, in the way in which we formulated that. But in some applications, instead, they are populated by continuous variables, right? So they vary in a continuous domain. Most frequently, design vectors are hybrid of those. So there are some variables that are discrete, some variables that are not discrete, are continuous. So you have to be able to deal with both. The size of the trace space and the type of the design vector are main drivers in the selection of your enumeration method. And this is really similar to what people in the optimization community face, right? So, for example, heuristic methods are more suited for, if you have to deal with discrete variables, much more than, with gradient-based methods for enumeration. Why? Because gradient-based methods assume the concept of gradient, that there is a gradient in the trace space, but instead, for example, if you have discrete choices, for example, prevalent type A versus prevalent type B, there is no gradient in there, right? So you have to use for example, some enumeration method if you're thinking of partial enumeration that does not use the concept of gradient. So principle number one, if it's possible, first always do a very simple architecture model in which you can do full enumeration. You will have a chance to make it more complex later, but at the beginning do something simple. Principle number two, maximize the information density in your trace space. Principle number two is to maximize the information density in the trace space. Really try to minimize the trace space size as much as possible without compromising the content in terms of information. So it's really important to keep information, as dense as possible. Now let's comment a little bit about partial enumeration. This can be used to explore very large trace spaces for which full enumeration is not possible. You would learn much more about this if you were to do a course, for example, in multidisciplinary optimization, which, by the way, you can find courses online. For example, on OpenCourseWare at MIT, you can find a good course on MSDO, it's called Multidisciplinary System Design Optimization. So partial enumeration, the way it works, well, first, typically, you enumerate some architectures. You evaluate them. Then you choose which regions, which subset of solutions, architectures are interesting to you. And they form sort of a guide to say where to look further, right? And you will look further. And you will keep doing so until you meet some termination criteria. For example, you have a finite time to do your exploration, or maybe you reached a good enough solution, and so forth. Right? If the termination criteria is not met, your algorithm has some sort of guiding principle that tells where to go next. Right? Otherwise, if the termination criteria is met, the exploration is ended. Right? So tools to do this, as said before, there are gradient-based methods. For example, sequential quadratic programming. So it's the same tools you use in optimization, if you think about it, because as I said before, you have design vectors. We'll talk later about evaluation. This will be done with objective functions. Heuristic algorithms. So you can have, for example, the genetic algorithm, very famous, very used and misused, unfortunately. Particle swarm optimization and others. Right? Literature references for these methods. Well, artificial intelligence, search methods, multi-objective optimization methods. There are several online resources that you can look to if you're interested in this topic. I mentioned about the MIT course, and I think that the course code is 16888, Multidisciplinary System Design Optimization. I think you can find it on OpenCourseWare. There are also very good webinars that are made by MathWorks, the company that produces MATLAB. You can just go and look, for example, on their webinar on global optimization, which is a very good reference to look at.